Good job for that. That's not a usual uh, like name that people can pronounce very well.
Thank you.
Yes, so without further ado, I'm going to present to you today a case study of a project that I've done in collaboration with ProRail, so the infrastructure manager in the Netherlands. And the idea there is that it came out of a, let's say, project that started within my doctorate, as Richard really introduced in the beginning. And I'm going to start off by going through the motivation, so the problem statement of the project or of the idea itself. Then we'll look at the applied proposed solution and what we did there. And then finally, we'll go through some conclusions, and hopefully I can give you some time to ask some questions or, yeah, have a nice discussion towards the end. So of course, it's a railway related presentation, so you're going to be seeing a lot of these animations through the presentation. And I really want to start with motivating the problem, and I always do it in a similar way so that everyone can kind of understand the need for this, and hopefully you're all on the same page as me after this problem statement. So I always start by motivating it and giving some food for thought with a, let's say, an analogy. And imagine you're really sick and you go to the doctor, right? They check your fever. Turns out you have a high fever. That's what we would call a symptom. And more often than not in the Netherlands, I don't know how they do it in the UK or how the NHS prefers to maneuver around that. But more often than not in the Netherlands, you get a reactive solution, which is a painkiller, paracetamol, whatever. And then you could feel good for a while, right? Now, let's say the next week you felt even worse than when you first went to the general practitioner. What a good doctor at this point would do, I hope so at least, is start to gather more information rather than just this high fever that was there in the beginning, rather than that symptom, such as your heart rate, for instance, maybe an MRI for some reason, blood tests, glucose test, whatever. I think you get what I'm trying to, the point that I'm trying to make right here. So again, I started with a analogy from the medical field. And what I wanted to say there is that more often than not, if you're starting with a symptom that doesn't really portray the root cause of what's going on, you would need extra information from different sources and from different data sets to really understand what is going on with a human body, right? And of course, I'm here to talk about the railway, but before that, I really want to give you a parallel of the human body itself and maybe the medical field and infrastructure in general. And I always compare infrastructure to the human body, and I really don't think it's a very crazy comparison, let's say. And to motivate it further, let me just give you some examples. The human body itself is made of different organs, and it's a system, right, that is behaving according to uh, some rules. And of course, as that system, it needs to have all these different components that are behaving as well in a specific way. So for instance, within that entire system, you have the brain, you have the liver, you have your heart, etc., etc. All of those come together for the human body itself as a system behavior. Now, I think that's very similar to infrastructure as well, or specifically rail, where you also have these different components, again, such as the fastener, such as the rail, the ballast, uh, I don't know, the subsoil, really different elements, different components that I would say are similar to organs in a human body. But not only that, in a human body, if you look at the medical field again, if someone, God forbid, had a rare disease, to really understand what's going on there and to qualify the root cause of that and to go to a diagnosis, you would sometimes need different specializations that understand these different components. And what I mean by that is a lot of the time cardiology, neurology, endocrinology, etc., all these different medical specializations are really needed to come together for a root cause analysis in case you had something quite rare. So again, I see that similar to rail, where I already told you about the components and the different organs. That's one similarity. Another similarity is these different knowledges that are needed and these different specializations. So similar to how you need a neurologist, a cardiologist, endocrinologist, whatever, you would also need different trades and different understandings of engineering to come together to really understand the railway track as a system, right? And that could be geophysical engineers, that could be geotechnical engineers, structural engineers, electrical engineers, sometimes, most of the time, drainage engineer, climate experts. I don't want to leave anyone out because I realize there's a big crowd here, but I think you get the point. So infrastructure and the human body are quite similar, and really to understand the system, you would need to dive into the components, but also into the different specializations and expertise. So unfortunately, that is not what is happening within the railway industry in terms of maintenance. At least I can say that for the Netherlands. And more often than not, maintenance is decided upon based on one component, which is the superstructure itself. And what I mean by that, so I already highlighted it, and I know this is not a accurate cross-sectional representation, but I generated something with AI, so you'll excuse me there. But what I'm trying to say with that is that really more often than not, instead of looking at the system and diving into the different components, what we are using in the Netherlands and in different parts of Europe is one component analysis and looking at the loss of alignment. So really in terms of cross level, height, or longitudinal level, as you would call it, twist, alignment. So really in the different angles and in the different um, I would say, yeah, and the different components vertically, horizontally, etc., etc. That is really describing to a certain extent that superstructure and that railway, how much it's lost its alignment. Of course, there are underlying causes for that, and that's what I'm interested in. But because we only look at that for maintenance, I say that that leads to a reactive and siloed maintenance. And again, let me look deeper into that or discuss it further. When you are looking purely at that one component analysis in terms of that superstructure, how much it's lost its alignment, it can lead you to, again, that reactive siloed maintenance. And I'll give you an example. More often than not, you send a tamper, it's adding ballast, it's fixing the alignment according to this geometry right here, to this relative track geometry. But let's think together and let's assume that, again, this is a very common problem in the Netherlands, that you have a part or a section that is on very weak subsoil and has a very weak foundation. And the loss of alignment is being generated again and again because of that. So because of this weak subsoil, you're really having your railway alignment, so portrayed in this data set, as being non-satisfactory, and you're sending the tamping machine again and again to fix that problem. But let's assume, as I told you, that the subsoil itself is weak. So what you're doing there is really, by adding more ballast and fixing that alignment, is adding more weight to a very weak foundation. So you're not fixing the problem, you're just making it worse. So again, this is what I mean by a reactive and siloed maintenance. And to go back to the introduction, this is basically similar to looking at a symptom and giving paracetamol as a reactive measure. Now, it's not that you don't need paracetamol or you don't need that painkiller. Of course, after surgery, you would need it, but knowing when to give it and when to do something different, I think is very important. So enough talking about the medical field. Let's discuss the case study and how I brought these ideas to life in a project. And what you see here is the headquarters of ProRail in the Netherlands. And continuing along the same lines and the same metaphor, they came to us and they were complaining that they had a sick track, or a track that is sick with embankment problems. So they needed some help, and they had a lot of data there, but they didn't know how to look at it. And that track is basically on what we call the A2 corridor, basically from a track that is between Culemborg and Tricht. And of course, we replied, as Fugro, we will do everything at our disposal so that you can be doctors towards your asset. And this is basically what we are trying to do here. And we used a framework that I call Smart Sectioning Framework, which is a 4-step framework that really looks to gather all the relevant data about the components, makes sure to gather some sort of knowledge and expertise by sitting with the people who have worked with the data or the people who are on the track, sectioning the data, and we're going to look at these different steps, and then adding even more data on top of that, and finally having it all in one place in a dashboard for better maintenance support and better maintenance decisions. So just to reiterate things, and I'm going to be doing that before I get into the crux of what we had done there. What we are really trying to do is to go from symptom to root cause, right? I think I've motivated that enough. And the way I see that is to really create, let's say, a dashboard for doctors by doctors with all the relevant information. And when I say doctors, of course, you can substitute that and put maintenance engineers or railway engineers. I think you get what I'm saying. So what I want to do is to go again from the symptom, which is relative track geometry misalignment or loss of alignment of the railway track in a relatively measured manner, which if you want to look at it from a pavement engineering perspective, it could be cracks on the pavement, for instance. That is the symptom. And I would like to go into, let's say, more of a Fitbit understanding of my asset. So really kind of right now, Whoop is a very popular wristband that you can wear, and it will show you everything about your heart rate, your sleep, etc. So I'd really like to get from that kind of one component analysis to a really holistic overview, holistic understanding of what's going on. Of course, with the main goal to answer the why. So why are we having these problems, these symptoms, and where, right? Why are we having them in this place, in that place, etc., etc. So to do that, to achieve that, you would need a lot of things, and I've already hinted to that. Some internal data from our company, from the likes of ProRail or Network Rail, monitoring data, so IoT data, open source data, internal expertise and knowledge, that's also very important, or even external, and collaborating. And when I say collaborating, that's something very important because you need to break the silos within departments, within Network Rail, within ProRail, within Fugro even, where I'm working. And that's really so that you can capture a lot of different expertise and put them into one place and make sure that everybody gets their say. So to get to the applied proposed solution, I wanted to just remind what we are doing. I've already done that a couple of times, but I think it's very good if everyone is following with me and I don't lose anyone, of course. So we're combining different information and knowledge about a linear asset from different sources with the main goal to understand more about it currently and in the future in a holistic manner. So really similar to what I told you about the human body, to look at the different components and the different medical specializations, but in the railway engineering field, with the main goal to capture root causes of the behavior. So to come to a diagnosis, if we bring it to the medical field again, leading hopefully to more informed maintenance and or research decisions. Again, you can bring that to the medical field, hopefully leading to a longer life cycle and less life cycle costs. So at the heart of all of this is what I call smart sectioning, which came out of my doctorate between where I collaborated with Fugro and the Technological University of Delft. And of course, I have some pauses within the presentation because I tend to speak quite quickly so that I can have a bit of a quick drink of water before going on. And this is, let's say, the more technical part. So I already motivated why we are doing this. I told you to a certain extent in general how we are doing this. Now let's dive into the data sets that we had at our disposal. And then I'll show you what we did with it and the final end point of all of that. So the first step, again, is to really understand what we are looking at. And I told you that ProRail were having problems with their embankments. So that is already a hint that will really guide all of our decisions in terms of the data that we will use and how we will section that data. So of course, it all starts from the soil. And at least in the Netherlands, So we had a lot of open source data CPTs that we collaborated internally with the geotechnical department to create a 3D ground model of that area. And it looks something like this. So this is the entire area. That's the Culemborg station over here and the Tricht station towards the other end. And of course, there are some assumptions that need to be made because you don't have the CPTs that are very resolute along the entire stretch of track, but it's a good place to start, I would say, to really look at these CPTs and look at the changes of the subsoil and the different layerization, where you can look at really uh, what type of layers do you have at every single location, how thick they are in terms of subsoil, how deep, etc., etc. So that was the beginning phase in terms of a data set. A second data set that was used is a data set from a company that is based in the UK, or they have some colleagues in the UK. And it's basically some satellite L-band, so different, I would say, low resolution, maybe active source screening, where they are able to infer the soil moisture up to, I would say, 1 to 5 meters of depth. To a certain extent, you would have to, I would have to look deeper into that a bit more, but that's about right, I would say. And from that remote sensing technique, they are really able to kind of infer the moisture values or how much moisture there is in the subsoils that are within that top layer. And we already know that for embankments, that's something that is quite important. The level of saturation, and more often than not, also the level of evaporation of that water, especially if you have a lot of compressible layers such as clay or peat, because that change of volume and those extra pore water pressures a lot of the time can lead you to some failures. So that's the second data set that we used, and we had it for different dates. So for 2022, May 2024, July, and November as well of that year. So another data set that was very interesting came from a company called Focus Sensors, and it was basically looking at fiber optic data along the railway track. And I thought it was a very interesting data set because we already know that uh, more often than not, fiber optic is being used for acoustic sensing and to infer some shear wave velocities from there. But this time it was used for movement sensing. So basically, every time a train passes, that movement is measured in terms of a strain, and it is recorded maybe, I don't know how many times a day. I would say definitely every time a train passes, but I'm not sure if they were doing it in between. What I had in terms of a data set was mean values of the middle of midday and the second part of the day. So really when the trains were passing. And I was able to use that data, which was a temporal data set from April to November 2024. And we looked at climate data, and that came from collaborating. Again, as I was telling you in the beginning, it's important to include the different medical specializations or engineering specializations to make that analogy again. And I talked to the hydrologists within Fugro, who are always working very closely with the government to be able to analyze slope stability for dikes and levees, which is a big topic in the Netherlands. And the embankments, to a certain extent, are a very similar construction, right? There's, of course, different loading parameters, that's obvious. But in terms of philosophy and in terms of design and stability, it was them with whom I consulted. And they told me to look at precipitation, evapotranspiration, and temperature as well. And the philosophy there, again, is that if there's a lot of drought, that change of volume within the layers can really start affecting the embankment and, of course, the subsoil that is under it. So we had a climate station, as you would call it, a meteorological station that was close by, and we got and extracted the data through an API to be able to understand what is going on within that specific time that we were looking at. And Other data sets that are interesting, of course, we looked at relative drag geometry, and that's basically the data set that is that I showed you in the beginning. Let's call it the symptoms. So that loss of alignment of the track. We looked at construction characteristics. We used the network model of ProRail. I looked at small wavelength irregularities as well, such as insulated block joints, weld locations, any type of small wavelength irregularity that is known from the construction side. I try to include it because we know that when a train passes at very high speed along that small irregularity, it causes a very strong impact load that hits and hits a PSS layer, which is something that I will explain in the next slide, and special structures. So special structures are basically just civil constructions, bridges, culverts, any type of civil construction that creates a interface and a transition zone in between. So a lot of data, a lot of information that was deemed relevant for embankment stability purposes. And of course, I promised you to explain what a PSS layer is. Everything here is written in German, so you're gonna take my word on what I'm saying based on that. But it's basically a layer of different materials that is constructed. So let's say this is the superstructure, the railway track itself, the ballast, maybe the sub-ballast layer. And between it and between the underground, you have what is called this PSS layer or prestatie stabilisatielaag. So it has to do with stability. And again, just to make sure everyone gets this, it's some sort of a cementatious layer with a gradation that is known. And it's there for water drainage purposes, for filtration, for load bearing, for structural support. But it's very important to note that it's really a constructed cementatious layer. And it wasn't constructed all over the railway track. It was basically put on specific areas. And I had that information, so it was only on a specific parts. And I won't spoil too much, but this was a very relevant data set to look at, and I want to show you later in the demo towards the end. So remember this type of data set and remember this layer because it's going to be quite relevant towards the end. Another data set that we used was RILA data. So basically the company I work for, Fugro, has this system. And based on that, you can do a lot of things. But what I used it for in that regard is because the data was train travel direction, and the data that I had from ProRail did not really have that in an automated manner. And for transition zones, it's something very important because if you go from soft soil to something stiff, it has different behavior than vice versa. So that was something quite important to capture. Okay, so a lot of data, but now what are we going to do with them? That's, of course, a very relevant question. More often than not, the more data that you have, the more headache that you have, because a lot of the time it's not information, right? How are we going to turn them into information? And this is basically the core and the framework and let's say the motor behind the all of this project and what came out of my doctorate. And it is what I call smart sectioning. So just to make you understand it in a very simple manner, I know that in the UK, it's a similar way of working than in Europe. And that relative track geometry that I explained in the beginning, so this loss of alignment or this symptom data is gathered for every 25 centimeters in Europe and every 20 centimeters in the UK. Now, we're talking about thousands of kilometers of track. How are you going to look at every 20 centimeters and make a conclusion? So what is usually being done is you create what we call a fixed section. So a section of a fixed length could be 50 meters, 100 meters, 200 meters. And that is, again, part of the standards and what is being used for the Netherlands and for the UK. And once you have that 100 meter, 50 meter, 200 meter section, what is being done there is you average the data in a standard deviation or you do some averages or you do some statistical methods so that you can describe that section into one key performance indicator. And based on that, maintenance is decided. Okay. So I don't like that method, to be honest, that fixed sectioning method, and I'm going to show you exactly why. So imagine that this is a 50-meter fixed section, and of course it is somewhat random the way you create these sections. And immediately I'm going to tell you that that's not a good way of working, that random fixed sectioning. But of course, there are philosophies in terms of why it is pushed in the standards, and we can discuss that later. And these are good reasons that they have, but my reasons are different, and I'm going to tell you exactly why. So let's assume that indeed this is the 50-meter fixed section. What happens here, if you're sectioning this in such a way, is that you're taking 3 behaviors and averaging them into one. And these behaviors are the bridge itself, the transition next to it, and a bit further than that. So this is basically what I'm talking about. Of course, you can look at it in the same way on the other side, but let's focus here for now. So what you're technically doing here is you're averaging 3 behaviors into one and having one key performance indicator to decide on maintenance for that entire section. Now, again, you might already have realized that I'm really fond of the medical field in terms of analogies. I really think it puts things into perspective quite well. If I were to describe that or to make a parallel or an analogy of what is happening here in the medical field, it's like me and Richard, for instance, and Stuart as well, going into the doctors. They get the temperatures of all 3 of us. Only mine is very high temperature, or only I am very sick. But because of the average, it becomes a lower average because Richard and Stuart are doing well. So because of that, we're all getting a very light treatment instead of me having my own tailored treatment and Richard and Stuart being sent back with nothing. That is kind of what is happening in that fixed sectioning methodology. So what I propose instead is to really do it in a tailored fashion, to take that information of that behavior and to do sectioning something similar to this. So where we know the transition zone is going to behave in a way, the bridge in another, and then the conventional track in another way, I really try to capture that in a section. And instead of having these fixed random sections, we have dynamic sections. So this is really what is smart sectioning, and this is the motor behind the combination of all the data. So to show you how that works, I made some animations just to be able to make you understand. And this is, let's say, a description of it. Let's assume these are the relative track geometry or the 20-centimeter points that you need to section. And you have the tracks colored in different ways according to the different construction characteristics. You have a lot of data from everywhere. I make these 20-centimeter points inherit the information they sit on, and then depending on how they are in a row, I try to create, and you can see the different colors now, I try to create somewhat homogeneous sections, again, according to the failure mechanism we are looking at, so embankment stability, and according to the deemed relevant data there. So that's where the expertise comes in. And we come back with something like this, with dynamic sections with different lengths, hopefully with each one of them having their own homogeneous behavior according to that failure mechanism. And on top of that, then we can add a lot of data. And the beauty of this, and you're going to understand it later, is that if each section is homogeneous according to that behavior and it has that data enriched upon it, then you can really start to compare the different sections. So you know what this section is made of in terms of soil, you know what its construction characteristics are, but you also you can use that and compare to the output data, to the symptom data, and see why that is behaving differently than another section. So it's really that tailored analysis, right? So instead of really averaging different behaviors into one, you're looking at behavior per behavior. But not only that, then the historical data, I would argue, per section. So if you have a lot of historical data with respect to time, that data per section, you can train it and predict how it's going to behave with respect to time. Because again, we can argue that that data set or that section in itself is homogeneous in behavior. So you can assume that the past will somewhat resemble the future. Of course, there's always surprises, but that's something you can sometimes train for in case you get one of these surprises. And you can also compare it with other similar sections somewhere else. But I really like this way of working. It helps you get to root causes, and I'm going to show you a demo at the end because, of course, I've been talking a lot with abstract things for now. And what we used for, in this case, to section, and that had to do with the data sets that I had uh, access to. Of course, if I had access to more data, I would have used it. I'll give you an example. I couldn't get access to maintenance records, and that comes down to the fact that ProRail is subcontracting these to maintenance contractors, and then more often than not, you'd have to go to a NDA or a confidentiality clause to be able to get that data because it could hinder the way these maintenance contractors are doing their business, but that's a bit of a tangent. But the data that we used were local velocity because the faster a train goes is allowed to go over a specific part. Of course, the stronger the forces and the dynamic amplification factors are going to be there. The subsoil type from the 3D ground model, ballast type. We wanted to use rail type, sleeper, and fastener type, but those were not updated. And as you know, if you load a lot of wrong data into the model, it's not going to behave the best. Transition zone data, depending how close you are from the special structures, switches and crossings, I used a maximum of 200 meters, the PSS layer, and I had a minimum section length as well. So those were used to kind of break down the sections. And afterwards, once we had these somewhat homogeneously behaving sections, we started to add extra data, which is a lot. I won't go into all of them, but fiber optic data, the symptoms from relative track geometry, some equivalent stiffness KPI, the moisture data that is there, the climate data, etc., etc. So really a lot of extra information was added on top of that. But not only that, once these sections were there, we were able to use a model that came from a very nice paper that was written by two researchers that work within Arcadis, UK, and they tried this for network rail, and it's an embankment instability model. And basically what it does is it compares right rail vertical deformation versus left rail vertical deformation. And if you guys can look at my screen, at me, just to make you understand what is going on there, let's assume you're driving straight, right, that way, and you're on an embankment, and the embankment edge is on your right. If your right rail is going down more than your left rail, that means that you're going through what we call a shoulder earthwork deformation. However, if your left rail, which would be towards the middle, is going down more than your right rail, again through vertical deformation, that would mean that you have somewhat of a deeper rotational embankment slip, which is not pretty, I can tell you that. It's quite a scary thing. And we use that model according to the data that we had. And one of them, remember, red is bad, black is also bad, but less bad. And yeah, so that was a data set that was used or a model that was also included. And then finally, with all of that, we can get to the demo. And I'm going to show you exactly what we were able to achieve towards the end. So this is the area that we were looking at, and immediately you can see some red and some less red areas, some white areas, which are somewhat better. These are all the different data sets that are there. We'll explain them once we get into the interesting case that I wanted to point out. Of course, I'm cheating because I've already worked a lot with the data, but I already know which one I want you to look at. It's this section over here that is very red. And first, let's go one by one in terms of the data that you have. So right here, you can choose between all the different relative track geometry parameters. So this symptom, loss of alignment, you have vertical deformation, height, hoogte in Dutch. You have shift or horizontal alignment, and they're within different wavelength domains. That doesn't matter, but you can choose them and look at them one by one. But for the sake of this demonstration, I would like to look at left and right rail deformation, just so that we can look at that model that I explained. This is fiber optic data with respect to time. These are the recordings. The bars are the averages across other sections so that you can compare, okay, what's happening with this section for every single month compared to other sections. So again, that's really that doctoral behavior to understand, okay, is this on the good side statistically or the bad side? That's the same right here. One is an alarm. So if you have a very sudden change, it causes an alarm. These are maximum values of fiber optic data. And these are data sets having to do with the climate values and correlated with fiber optic data. I won't get too much into that because I want you to focus on some elements here. And of course, once you hover over the section, you can see a lot of different information. If you focus towards the middle, you find ballast type. Steenslag is crushed stone. 3550 would be kind of the diameter of them. How many insulated block joints are within that section, whether it's on a PSS layer, 0 or 1. Again, I told you to remember that layer because we're going to get to that. The soil summary model, so how much vein is peat, basically, how much sand is under it, how much clay, soil moistures from the L-band data, and there's something called homogeneity index. That's a bit of a more difficult explanation, but in case you're interested, I can explain it to you once I'm done. And of course, again, if you go above the soil summary model, you have whether it's on a transition zone and whether and related to the train driving direction. So just to show you an example, we already know that this should constitute a transition zone. If you hover over it, you can see a lot of clay, by the way, under it, around 5 meters, which is not a good thing. Somewhat a lot of peat, but you can see that right after it, you have a concrete concrete rail viaduct. Spoor is rail in Dutch. So just to come back to that example that I had chosen for you, and again, it is very red compared to the other parts. Let's look at the right rail versus left rail deformation. And as you remember, red is very bad, so it's going through that rotational slip within the middle, and it's not a good thing. In case you think this is something normal in terms of left rail versus right rail deformation, I'll show you a track that is behaving somewhat more normally, such as this maybe. This is less normal. Maybe this, so quite close to each other. They shouldn't have that much difference. These are the maxima as well. But again, let's get back to this. You see this kind of diverging behavior in terms of the data set, and this is with respect to time. And again, this is something very concerning. Now, the first question that this is supposed to answer is why? Why is this happening? We have a lot of information. What is going on? Why do we have that? So let's go deeper and zoom in. You see that the PSS towards the middle, I cannot use another mouse, otherwise I would have loved to show you with the laser pointer. But if you find the PSS layer is 0, and then the section afterwards, it's immediately 1. So I let you think of it for a bit, but some of you might already have the answer. Again, you see the amount of peat is 0.2, and the average amount of clay under it is 3.4 meters. And then suddenly you see a 1.4 meter thickness of peat and 4 meters thickness of clay within that section. So just to tell you, I'm going to give you the answer because this is not an interactive session. I'm basically talking to myself, but what is happening there is another transition zone. So you're having a part that is much more stiff with less peat, less clay, which is right here. But immediately after, and you also have that PSS layer, which is that layer, that cementatious layer that's for stability purposes, for strength, etc., etc. But immediately after, so here, sorry, I'll retract what I said. So you have the soil that is somewhat more strong or somewhat more sturdy in that area because less peat and less clay and no PSS layer. And then immediately you have a PSS layer and weaker soil. So what is happening there is this transition zone, first of all, because of that PSS layer. And second of all, because of that those compressible soil layers that are changing in terms of volume with respect to time and changing with respect to strength. So within that, it's basically similar to a transition zone that would be a viaduct or a bridge or anything that is generating even more dynamic effects. And again, because I want to have a discussion, I won't go to into other areas, but you can see a lot of sections exhibiting similar behaviors that are on transition zones, such as this one. Again, such as this one as well, which is on a kind of bridge or viaduct. But here you have even more transition that comes from the water on the side. Anyways, I wanted to show you the real value of this is to be able to dive into the symptomatic data, but also dive into the data that describes this section so that you can give some sort of a root cause understanding and compare sections to really know what is going on. So looking at the time, I will get into conclusions. And of course, there are many benefits to this methodology. I would like to keep, let's say, more than 10 minutes for questions, so I'll rush through them. But one thing that you can do, because you have this data model where everything is kind of interconnected per section, per behavior, is you can run a feature importance analysis using information theory or using AI, machine learning, let's say, to understand what is affecting a specific output the most. So it could be that the subsoil type, could be transition zones. You could do the same with correlations. You could do some sensitivity analyses. Even per section, you can run some Monte Carlo analysis because it's a homogeneously behaving section to fill in gaps of missing data. You can do really so much. You can build a machine learning model or forecasting model per section. You can have tailored research and maintenance advice per section. The world becomes the oyster. At the end of the day, this is really to unlock predictive maintenance in the future and to have that data model to do that. Of course, something I want to say is that this methodology is not a set in stone methodology. It's more of a framework, which is what I started off by saying, because it will really depend on the data sets that are available. It will really depend on what type of monitoring data that there is, what are the needs of the infrastructure manager. So what is the problem there from the first case according to different reports. But it really will help you highlight and tailor your maintenance to different assets along that track differently. So I would say currently we are at an isolated understanding of root causes of degradation, and that comes with the likes of ProRail receiving different, let's say, reports from different data providers, looking at one data set or one component data set to actually make their maintenance decisions. What I would say we achieved with this is a quasi-holistic understanding of this degradation. We made some steps to reach that holy grail of predictive maintenance, but where we should go, and that would be maybe my closing advice, is to a full understanding of root causes of degradation. To get there, you need to even add more data sets, such as axle box accelerations, any IoT data that you have, maintenance histories, groundwater tables, INSAR data, tilt sensors, geophysical data such as ground penetrating radar, seismic CPTs, etc., etc. So you have a framework to put everything together, which is what I'm offering here, but you really need to look at all these different data sets in more detail. And then you have this big data database that you can really start to analyze and run different automatic analyses just to understand more what is going on and to quantify what we sometimes already know, but maybe you can break it down in a more accurate manner. Of course, there's a lot of challenges to get there, and I had to go through them one by one. Different data formats. The data is most of the time very sparse in terms of time and in terms of resolution and space. Waiting for different data suppliers and having to talk to them. A lot of people don't want to share data, which is a shame because that's the only way we can get to this, again, holy grail of predictive maintenance. A lot of data errors that you have to sift through, etc., etc. With that, I've been talking for almost an hour. Uh, so I'll leave the floor open for some questions. I hope you enjoyed this presentation.
Yeah, Karim, that was really interesting. I think for me personally, I really enjoyed the way you could break down quite a complex sort of, as you say, like ethereal thing almost, and make it into quite a good analogy that really kind of brought it home and yeah, made it make sense for someone who was outside of what you were doing. So thank you for that. If anybody does want to ask questions, you can either pop hands up or I can see a few coming through on the chat now, so I'll work through those. Before we start that, I guess from my point of view, when you talk about dynamic sections and how you could use these differently, kind of quite interested in talking about KPI measures. Would you look to set different KPIs for different types of section, or would you individually baseline each one? How do you think that should be used?
Again, I really think it has to do with the failure mechanism. So that always has to be the basis of what we are doing. So here we were looking at embankment stability. So the KPIs had to reflect that. And one of them came from that embankment stability model that the Arcadis guys came up with. And uh, of course, you would need to use something similar for these different sections so that you can really compare and do that, have that understanding, okay, why do we have something bad here and not there? And then dive deeper into the data. Of course, you can automate this process, but I myself am really curious to get into the data myself. First of all, to see what is going on, if there are any errors, if things make sense. So yeah, that would be my answer.
Okay. Okay. So I'll go through some of the questions in the chat now. So
For
the first ones are from Aditi. So transition zones are related to soil changes or transitions to a bridge or any sort of change. So I think it's clarifying which one of those or all of them are you looking at?
Yeah, so the transition zones that we had created had to do purely with special structures and switches and crossings. However, of course, a transition zone in itself is really, let's say, based on two parameters. One would be that sudden change of stiffness. So really wherever you have that PSS layer that stops and ends, that should be treated as a transition zone. So that was a learning element for myself. But also wherever you have, let's say, a type of subsoil that suddenly changes, where you're going from something very stiff to something weak, like that really sudden change in stiffness. But another parameter is usually from that differential settlement that comes from special structures. So when you construct a bridge and you have an embankment or a normal railway on the side, there usually always is a differential settlement. Couple that with that sudden stiffness change, then you have really a classical transition zone. But I would again argue that transition zones could be many different things. Maybe somewhere where maintenance has not been done evenly, somewhere where you have that sudden change of geometry, also could be related to saturation, etc., etc.
Okay. And then a second question, are there fiber optics installed on each section?
No, so they didn't have it installed on the entirety of for this specific project, yes, but they don't have it installed, of course, all over the Netherlands. And that was basically the scope choice for myself. So wherever I had that fiber optic data, I chose to focus my analysis there. So within the scope of what I showed you, yes, but if you're looking at it from a bigger perspective, no, unfortunately.
Okay. Next one's from Steve Pearson. So thank you for the interesting presentation. Your first example appeared to simply show that the PSS layer type construction should have continued further over the adjacent weaker ground when the line was originally constructed. Does that ring true with what you saw, or is that slightly different?
Um, Somewhat, because what we realized is that this PSS layer was constructed on these weak layers. So the layers where you had a lot of peat, by doing my correlation analysis, I was able to find that the PSS layer was mostly constructed on those. So you had on one side somewhat of a stronger subsoil, and then suddenly a weak subsoil with a PSS layer. But what that PSS layer, and of course we know that soil changes with respect to time, especially if it's compressible, uh, changes with respect to the water and the saturation, with respect to the seasons that are there, how much rainfall, etc., etc. But what that ended up creating, this PSS layer, is an extra transition zone. So what I would advise is to treat it similarly and to be able to create a gradual change of stiffness rather than have it be very concentrated in one place, because we're seeing that it's creating a lot of embankment instability. And that philosophy of gradually creating that or gradually changing that stiffness is used in a lot of classical transition zones, so those special structures. So treating it as such would be my advice. And of course, I was really frustrated to not have those maintenance records, to be honest, because it's a lot of golden data, right? But
Yeah, absolutely. Okay, and final question in the chat at the moment is from Jonathan Lynch. How easy is it to upscale this method? How much does it rely on site-specific investigation positions, e.g. the CPT along the route, or are more remote methods appropriate?
yeah, look, this method becomes very easy to upscale once we standardize. And of course, it's probably a very classical response that I'm giving you, but once we standardize the data sets that are across an entire country, if you're talking about upscaling it to a country, to a nationwide scale, if we are able to standardize the data in terms of format, in terms of frequency, in terms of resolution, once we have that in place, maybe not in terms of frequency actually and resolution, but in terms of how it is being collected and in terms of the format at least, and which data sets you have where and when, then you can create this really um, interlinked data model. And then from there, based on the let's say based on the failure mechanism, you are able to create these parametric sections in an automated fashion and then go from there. And of course, we are at the age of AI and big data, so we are really empowered to do such things. But it all starts from the foundation of the data gathering and the standardization and making sure we have everything kind of similar so that we can really upscale it.
Okay, thank you. Just had another question drop in there. I can see we've got a few minutes left, so I'll go through that one if that's okay. From Seb Merricks, did you make any adjustments to account for the effective maintenance on the track, particularly for the track geometry in SAR data sets?
That's a very nice question because the effect of maintenance is very important for degradation modeling. However, that's not something that we looked into, but of course it is a very important parameter that could be created further because we already know that whenever you tamp a track or when you maintain it, there's the ballast memory effect, so it goes back to what it was before the maintenance, and the way and the speed with which it goes back has to do with the track parameters itself. So that could be something that was created, and also the effect of the maintenance and how effective it is also something that we can add, but we can always infer when maintenance occurred from the data. But the data in terms of relative track geometry was spaced by 6 months. So there could be a lot that happened in between that we don't know about. So having those records would have been amazing. And in terms of INSAR, we did not use INSAR for this specific track. I used it for my doctorate. I wrote an article about it actually on a PWI journal that you can read where I did use INSAR. So yeah, I hope that answers your question.
Okay. Thank you for that. So just to close out, then a few final bits to go through. Again, kind of as I said, as you were closing up there, Karim, thank you very much. I think you made, as I say, quite a complex sort of series of concepts very easy to understand, and the analogies definitely helped with that. So I definitely like the Fitbit of asset understanding. That definitely rings kind of somewhere as kind of how these things should be. So no, thank you. Um, If anybody does have any further questions, if there's things you'd like to kind of take onwards, the PWI will set up a kind of on their LinkedIn page, they set up a dedicated discussion post for each of these. So pop over there, have a look, keep the conversation going. I'm sure everybody would kind of like to get involved with it. So. And then last of all, a reminder of the couple of upcoming events I mentioned earlier on. So the next one of these Lunch and Learn events is the 24th of June, and that's Transforming Cambridge South, a journey from vision to reality in infrastructure enhancement. And the 2nd of July PWI Technical Conference, which is electrification and innovation, rails path to decarbonisation. And if you're interested in tickets, sponsorship opportunities or exhibitor opportunities for that, pop over to the PWI website and you'll find all those there. But thank you very much. Thank you all for attending. I think we got up to about 120 people at kind of the peak there. So really good attendance and yeah, thank you and see you again soon.